So this is the initial feasible solution that we had achieved using the Vogel's approximation method. Now, step number 3 is to test the initial feasible solution for acceptability. Now, there are two conditions to test for acceptability. The first one is that number of allocations should be equal to m plus n minus 1, where m is the number of rows and n is the number of columns. So in our case, m is 3 and n is 4. So this becomes 3 plus 4, 7 minus 1, 6. Now let's count the number of allocations. So 1, 2, 3, 4, 5 and 6. So number of allocations is equal to m plus n minus 1. So this condition is met. Now the next condition is that these allocations should be in independent positions. Now what this means is that it is not possible to change any individual allocation without either rearranging the position of the allocations or violating the capacity and demand constraints. So a simple rule of thumb for allocations to be in independent position is that it is impossible to travel from any allocation back to itself by a series of horizontal and vertical jumps from one occupied cell to another without a direct reversal of the route. So let's try doing that for this square, which is Chicago to Denver. So let's start from this and then let's try to come back to this square, forming a closed loop using horizontal and vertical jumps from one occupied cell to another. So let's start from here. Let's go here. Then we can take a 90-degree angle from here and come down. Then we can go here. Now from here we can't go to any other cell without reversing the route, which is not good. So basically this is in independent position. Now again, if we try, from here, if we come down to this occupied cell and then come to Houston, Miami, again from here we can't go to any other occupied cell and then come back to Chicago, Denver. So what this means is that Chicago, Denver, this square is an independent position. Now if you try the same thing for all other allocations, you will find a similar pattern. That is, all the allocations are in independent positions. So basically both the conditions for the acceptability test are met. That means that we can proceed with the optimality test now. Let me clean up these lines here to proceed with the optimality test. Now for the optimality test, there are two methods, the stepping stone method and the modified distribution method. So we'll use the stepping stone method here. Now the first step in the stepping stone method is to proceed row by row and select a water square. Now water squares are the squares without any allocation. So let me note down the water squares here. I'll use the first letter of the name of this city to denote the location. So Chicago, Miami, I'll just say CM. So the first square is CM. The next is Chicago, Jackson, so CJ. The next one is Houston, Lincoln, so HL. The next is Houston, Jackson, so HJ. The next is Buffalo, Miami, so BM. The next is Buffalo, Denver, so BD. Now the next step is to establish a closed path using rectilinear motions, that is moving horizontally and vertically only, starting from the selected square via the stone squares. Stone squares are the ones with allocation. So via the stone squares and then back to the same water square. Now we can make a right angle only at the stone squares, even though we can skip over stone and water squares. So basically we are doing the same thing that we did earlier to check if the allocations are in independent position. The difference is that we checked the allocations to be in independent positions for the stone squares, that is squares with allocations. Now we are doing for the squares without allocations, that is water squares. So for the first one, the closed path will be Chicago, Miami to Chicago, Denver to Houston, Denver to Houston, Miami, and then back to Chicago, Miami. So this can be CM, CD, HD, HM. The next is Chicago, Jackson. So the closed loop will be Chicago, Jackson to Chicago, Lincoln to Buffalo, Lincoln to Buffalo, Jackson, and then back. So this is CJ to CL to BL to BJ. Now the next one is Houston, Lincoln. So the closed loop will be Houston, Lincoln to Chicago, Lincoln to Chicago, Denver to Houston, Denver, and then back to Houston, Lincoln. So this becomes HL to CL to CD to HD. Now the next one is Houston, Jackson. Now for Houston, Jackson, the closed path will be Houston, Jackson to Houston, Denver to Chicago, Denver to Chicago, Lincoln, then down to Buffalo, Lincoln, then to Buffalo, Jackson, and then back to Houston, Jackson. So Houston, Jackson to Houston, Denver to Chicago, Denver to Chicago, Lincoln to Buffalo, Lincoln to Buffalo, Jackson, and then back to Houston, Jackson. Now the next one is Buffalo, Miami. Now for Buffalo, Miami, the closed path will be Buffalo, Miami to Buffalo, Lincoln to Chicago, Lincoln to Chicago, Denver to Houston, Denver to Houston, Miami, and then back to Buffalo, Miami. So let's note this down. So Buffalo, Miami to Buffalo, Lincoln to Chicago, Lincoln to Chicago, Denver to Houston, Denver to Houston, Miami, and then back to Buffalo, Miami. And then the last one is Buffalo, Denver. So the closed path for Buffalo, Denver will be Buffalo, Denver to Buffalo, Lincoln to Chicago, Lincoln to Chicago, Denver, and then back to Buffalo, Denver. So let's note this down. Buffalo, Denver to Buffalo, Lincoln to Chicago, Lincoln to Chicago, Denver, and then back to Buffalo, Denver. Now the next step is to assign alternate plus and minus sign on the closed path, starting with a plus sign on the water square. So the first, which is the water square, remains plus. Then we put minus, plus, minus, minus, plus, minus, minus, plus, minus, minus, plus, minus, plus, minus, minus, plus, minus, plus, minus, minus, plus, and minus. Now the next step is to calculate the net cost change for the path. The net cost change is obtained by summing up the unit cost of each cell on the closed path. So for this one, the first one, Cm minus Cd plus Hd minus Hm. So the net cost change will be 7 minus 2 plus 1 minus 3. So 7 minus 2 is 5 plus 1 is 6 minus 3 is 3. For the next one, Cj. So Cj is 5 minus Cl is 4 plus Bl is 7 minus Bj is 4. 5 minus 4 is 1. 1 plus 7 is 8. 8 minus 4 is 4. For the next one, HL. HL is 5 minus Cl is 4 plus Cd is 2 minus Hd is 1. 5 minus 4 is 1. 1 plus 2 is 3. 3 minus 1 is 2. The next is Hj. So Hj is 2 minus Hd. 1 plus Cd is 2 minus Cl is 4 plus Bl is 7 minus Bj is 4. 2 minus 1 is 1 plus 2 is 3 minus 4 is minus 1 plus 7 is 6 minus 4 is 2. Now proceeding to Bm. So Bm is 6 minus Bl is 7 plus Cl is 4 minus Cd is 2 plus Hd is 1 minus Hm is 3. 6 minus 7 is minus 1 plus 4 is 3 minus 2 is 1 plus 1 is 2 minus 3 is minus 1. And the last one is Bd. So Bd is 9 minus Bl 7 plus Cl 4 minus Cd is 2. 9 minus 7 is 2 plus 4 is 6 minus 2 is 4. Now the next step is to evaluate the solution for optimality by observing the sign of the net cost change. So if you evaluate the net cost change values, you'll find that there is one value which is negative, which is for square Bm. So if there is a negative sign, then it indicates that a cost reduction can be made by making an allocation to this square. So this means that we have not yet arrived at the optimal solution. So now we have to iterate towards optimality and improve upon this solution. So the first step is to select the water square with the largest negative net cost change. So in our case, we only have one square which has a negative net cost change. So we'll select that square, which is BM, Buffalo to Miami. Now let me draw the closed loop for this square. So BM to BL to CL to CD to HD to HM and then back to BM, and then alternate plus minus sign. So this is plus minus plus minus plus and minus. Now the next step is to subtract the smallest of the figures from each square at the negative sign on the closed path and add it to each square at the positive sign on the path. So basically the next step is to move the allocation from the other allocated square to this one square which is not allocated, because it indicates that the net cost change of moving to this square will be negative. That means the total cost can reduce. So we have to find out, okay, how much is the minimum that can be subtracted from these squares with a negative sign. So the lowest one here is 30, right? Yeah, so 30 is the lowest. So the maximum we can allocate to this square is 30. So 30 we have to subtract here, so this allocation becomes 0. Then we have to add 30 here, so this becomes 45. Subtract 30 from here, so this becomes 55. Add 30 here, so this becomes 35. Subtract 30 from here, so this becomes 40. Let me cut the original allocations to avoid confusion. So now this is the new allocation for the improved solution. So let's find out if this improved solution is now the optimal solution or not. So this is the improved solution that we obtained after the first iteration. Let's first find out the total cost. So the total cost of transportation will be equal to the multiplication of unit cost of transporting per case multiplied by the number of units being transported. So 2 multiplied by 55 plus 4 multiplied by 45 plus 3 multiplied by 40 plus 1 multiplied by 35 plus 6 multiplied by 30 plus 4 multiplied by 50. 55 multiplied by 2 is 110 plus 45 multiplied by 4 is 180 plus 30 multiplied by 40 120 plus 35 multiplied by 135 plus 6 3s are 18 10 plus 4 5s are 20 and another 0. Now let's add this up. So unit place we have 5, tens place we have 1 plus 8 is 9 plus 2 11 plus 3 14 plus 8 22, 2 carry over, 2 plus 1 3 plus 1 4 plus 1 5 plus 1 6 plus 2 8, so $825. So just to remind you, the previous transportation cost that we had obtained prior to the first iteration was $855. So we do have an improvement of $30 here in the overall transportation cost. Now let's find out if this is our optimal solution or not. But before we do the optimality test, we have to first do the acceptability test to find out if we can proceed with the optimality test or not. Now there are two conditions for the acceptability test. First one is that the number of allocations should be equal to m plus n minus 1. Now we know that m plus n minus 1 in our case is 3 plus 4 minus 1, which is 6. And let's find out the number of allocations. So we have 1 2 3 4 5 and 6. So the number of allocations is equal to m plus n minus 1. So the first condition of acceptability is met here. Now the second condition is that all allocations should be in independent positions. So if you evaluate, you'll find that all allocations are in independent positions. So what this means is that we can proceed with the optimality test. So for the optimality test, we'll again use the stepping stone method. So within the stepping stone method, we have to first take all the water squares, that is the squares which do not have any allocation, and evaluate if there is any chance of improving the cost by making an allocation to those unallocated cells. So the unallocated cells here are Chicago to Miami, Chicago to Jackson, Houston to Lincoln, Houston to Jackson, then Buffalo to Denver, and last one Buffalo to Lincoln. Now let's identify the closed path for each of the water squares. We need the closed path because the closed path ensures that when we make an allocation to the water square, we balance out the other allocations so that the demand and supply constraints are not violated. So for Chicago Miami, the closed path will be Chicago Miami to Chicago Denver to Houston Denver to Houston Miami and then back to Chicago Miami. So this will be CM CD HD HM. For Chicago Jackson, the closed path will be Chicago Jackson to Buffalo Jackson to Buffalo Miami to Houston Miami to Houston Denver to Chicago Denver and then back to Chicago Jackson. Now in this loop we are skipping the Chicago Lincoln, which is a valid situation. We can skip over the allocated cells. So the loop becomes CJ to BJ to BM to HM to HD to CD. Now the next water square is HL. So the closed path is Houston Lincoln to Chicago Lincoln to Chicago Denver to Houston Denver and then back to Houston Lincoln. So HL to CL to CD to HD and then back to Houston Lincoln. The next one is Houston Jackson. So the closed path will be Houston Jackson to Buffalo Jackson to Buffalo Miami to Houston Miami and then back to Houston Jackson. So this becomes Houston Jackson HJ to BJ to BM to HM. Now the next water square is BD. So BD, the closed loop will be BM to HM to HD and then back to BD. So BD to BM to HM to HD and then back to BD. The next water square is BL. So for BL, the closed loop will be Buffalo Lincoln to Buffalo Miami to Houston Miami to Houston Denver to Chicago Denver to Chicago Lincoln and then back to Buffalo Lincoln. So BL to BM to HM to HD to CD to CL and then back to BL. Now we have found out the closed loop for each and every unallocated square. Now let's assign the alternate plus minus sign, starting with the plus sign assigned to the water square. So minus plus minus, minus plus minus plus minus, minus plus minus, minus plus minus, minus plus minus, minus plus minus plus minus. Now again these signs are allocated in order to balance out the supply and demand constraints. Now let's find out the net cost change for each of these squares. The net cost change basically will give us whether by making allocation to these water squares we are going to be able to reduce the total transportation cost or not. So for the first one, CM to CD, so CM is 7 minus CD is 2 plus HD is 1 minus HM is 3. So 7 minus 2 5 plus 1 6 minus 3 is 3. The next one is CJ. CJ is 5 minus BJ is 4 plus BM is 6 minus HM is 3 plus HD is 1 minus CD is 2. 5 minus 4 is 1 plus 6 7 minus 3 4 plus 1 5 minus 2 is 3. The next one is HL. So HL is 5 minus CL is 4 plus CD is 2 minus HD is 1. 5 minus 4 is 1 plus 2 is 3 minus 1 is 2. The next one is HJ. So HJ is 2 minus BJ is 4 plus BM is 6 minus HM is 3. So 2 minus 4 is minus 2. Minus 2 plus 6 is 4. 4 minus 3 is 1. The next one is BD. So BD is 9 minus BM is 6 plus HM is 3 minus HD is 1. 9 minus 6 is 3 plus 3 is 6 minus 1 is 5. Now for the last one, BL. So BL is 7 minus BM is 6 plus HM is 3 minus HD is 1 plus CD is 2 minus CL is 4. So 7 minus 6 is 1 plus 3 is 4 minus 1 is 3 plus 2 is 5 minus 4 is 1. So now we will evaluate the net cost change value. So all the net cost change values here for the unallocated squares have a positive sign. What this means is that if we make an allocation change such that we allocate to any of the unallocated squares, then the cost is going to increase. Had any of these signs been negative, then that would have indicated that the cost can be reduced by making a change in the allocation. So at this point, because all the signs are positive, we have achieved the optimal solution. So this solution here is the optimal solution, and the total cost of transportation is $825. Now again, let's not forget to multiply this total cost by 100 because the capacities here were expressed in terms of hundreds. So the total cost is equal to 825 multiplied by 100, which is $82500.